So, where did we stop yesterday? Methods of wastewater collection. The first one is conventional, the second is the correct one. Well done, Betsy. That's the best way to say it.
Thank you, Professor.
Now please come out to the board and tell me what that means.
With pleasure, Professor Higgins. The conventional method of wastewater collection dates back to ancient times, when wastewater was not cleaned or treated. Wastewater was just discharged and forgotten. This practice is still common today, where wastewater naturally flows downslope, ending up in the first body of water it runs into.
It is interesting to note that today the types of wastewater, regardless of their principles of formation, are not the same as they were centuries ago. Let's describe them. Domestic wastewaters carry everything related to human life: feces, urine, pharmaceuticals, detergents, and other household chemicals. Stormwater runoff, resulting from precipitation that washes man-made pollutants off of roads, urban and industrial areas. There are two types of agricultural wastewaters: wastewater produced by plant cultivation and wastewater generated by livestock production. The first contain organic fertilizers, mineral fertilizers, and crop protection agents. The second contain waste from animal and poultry farms. And finally, industrial wastewaters, which are often the most toxic. I'd like to reiterate that the conventional method of wastewater collection simply means that wastewater was not collected. Roughly speaking, various wastewaters simply flowed into random points of discharge and bodies of water. The second principle of wastewater collection includes three technological approaches. The first approach: diffused runoffs are united into one water channel flowing into a particular treatment facility. The second approach: toxic runoffs are united into one channel going into a specialized treatment facility. The third approach deals with domestic wastewaters. Since they can be slightly polluted or heavily polluted, they require different types of constructed wetlands. Slightly polluted domestic wastewaters are better treated by surface flow wetlands, and heavily polluted domestic wastewaters are treated by subsurface flow wetlands or hybrid wetlands. All of these methods help to collect wastewater suitable for biological treatment.
Thank you, Betsy. You haven't missed anything. Now, may I ask you to solve a problem? 500 tourists, including staff, are staying in a big oceanfront hotel. Every day, 600 cubic meters of the hotel's wastewater is released into the ocean. The hotel is served by a subsurface flow constructed wetland. The constructed wetland has the following parameters. Hydraulic retention time is 5 days. The porosity of the substrate is 50%. I'd like you to calculate the working volume of this constructed wetland, necessary for more effective treatment of domestic wastewater that enter the ocean. Is the task clear?
Yes, it is. I just need a few minutes. The working volume of the constructed wetland is calculated using the following formula. Daily water flow rate is multiplied by hydraulic retention time and multiplied by 100%. The obtained product is divided by porosity, expressed as percentage. If I haven't made any mistakes, a volume of 6,000 cubic meters is required for effective treatment of this domestic wastewater.
Your calculations are correct, Ms. Doolittle. However, I set a trap that you have fallen into. If you have divided the overall water flow rate, 600 cubic meters per day, by the number of tourists, 500 people, you would obtain that each tourist spent about 1,200 liters per day. That is more than 4 times as much as the standard consumption rate in developed countries. Thus, it's apparent for us that the influence is highly diluted. Maybe because of irrigation runoffs, or water from swimming pools, or both, Anyway, the optimal working volume of the wetland for this particular hotel compared to your calculations should be?
It should be 4 times smaller than my result. That's not 6,000 cubic meters, but just about 1,500 cubic meters. How stupid of me.
You shouldn't criticize yourself, Miss Doolittle. Let's get into our subject.
Okay.
Betsy, why did we choose this name for the subject? Constructed wetland within a landscape. What do we want to point out by choosing these words?
Firstly, wetland construction and design is always part of a landscape. Secondly, constructed wetlands ensure a smooth transition from an artificial landscape to a natural one.
And thirdly, unlike activated sludge systems, constructed wetlands do not require a sanitary protection zone, which separates them from residential areas. That's not all. Autochthone biocenosis of constructed wetland kills pathogenic microorganisms but doesn't harm beneficial microorganisms, which contribute to the treatment. Moreover, these beneficial microorganisms, together with the treated water, end up in natural bodies of water, where they continue cleaning. Thus, a constructed wetland is not only a piece of landscape, but also a part of the local ecosystem. To design a constructed wetland, technical engineers take the following factors into account: the climate and weather conditions of the region, the topography, the depth of the water table, the location of man-made objects nearby, the number of residents determining the wastewater volume, and the hydroecological characteristics of the receiving body of water. Nowadays, there are many engineering solutions to each of the above-mentioned factors. Let me give some examples. Seasonal and weather factors involve, firstly, the planning of emergency spillways for excess water during heavy rainfall. Secondly, some protection to reduce evaporation from constructed wetland during dry season. And third, thermal insulation to protect the constructed wetland from freezing in case of a sudden drop in air temperature. The design of constructed wetlands requires considering the topography to ensure a downward flow for both influence and affluence in order to move water downhill. Betsy, why downhill?
So as to avoid using pumps. Pumps would considerably increase the cost of constructed wetland operation and maintenance.
Exactly. The decision to build the constructed wetland below or above ground surface depends on the depth of the water table.
If the water table is at sufficient, precisely calculated depth, the constructed wetland is built below ground surface. And vice versa, if ground waters are too high, a wetland should be located above the surface.
Thank you, Ms. Doolittle. Man-made structures built into the landscape like what structures, Betsy?
Motorways or, for example, solid waste landfills.
Absolutely right. Stormwater runoff flowing down the motorways require immediate treatment. That's why a very long wetland, often many kilometers long, is sometimes constructed on either side of a busy road. These constructed wetlands effectively treat stormwater runoff to prevent pollution of the nearby landscape. Solid waste landfills are exposed to heavy rainfall. In this case, a constructed wetland surface should be located below the waterproof bottom lining of the landfill. Betsy, why do we need a waterproof bottom lining? And why does a wetland surface have to be below it?
When rainwater percolates the layers of waste, the outflow is a toxic mixture. A waterproof bottom lining is crucial to prevent the infiltration of this toxic mixture into groundwater. And if the wetland is placed below the surface of the waterproof bottom lining, the landfill runoffs inevitably get into the wetland.
Okay, let's carry on. The volume of domestic wastewater in this area depends on the number of its residents. And, as we have already discussed, this determines the working volume of the constructed wetlands suitable for this landscape. And then, lastly, self-purification of the receiving bodies of water, lakes, ponds, rivers, takes a short time only if we, wastewater treatment specialists, strictly follow certain hydrological, hydrochemical and hydrobiological conditions. Project engineers consider most of these conditions when constructing a wetland. Ms. Doolittle, Thank you once again for your clear-cut answers and comments. I have no more questions.
Professor, but may I ask you a question?
Of course.
Sir, could you give some examples of when effluents increase the biodiversity of a receiving body of water and improve its hydrological parameters at the same time?
There are many such examples, but now I will give you only one. The building of two integrated constructed wetlands at Qinghai and Danyaopi in Taiwan allowed for a considerable increase in biodiversity in the area. The number of bird, fish, and aquatic invertebrate species increased more than twofold. The landscape around these wetlands is now difficult to distinguish from a natural one.
That's amazing.
I agree. What's also amazing is how different constructed wetlands are from activated sludge systems. I will reiterate that the cement facilities of an activated sludge system also need continuous monitoring. 24 hours a day, operators regulate the processes in the air tanks. Engineers must constantly monitor the air blowers and mixers. Special technical services continuously oversee the recycling of the excess activated sludge, etc., etc. A constructed wetland, by contrast, is self-regulated. It's amazing how a constructed wetland is in itself a small ecosystem, which incorporates into the ecosystem of a particular area and supports its homeostasis. For example, by discharging into a pond or lake, a constructed wetland can considerably contribute to plankton growth, which creates perfect conditions populating the water body with fish. In addition, a carefully landscaped wetland is a comfortable habitat for aquatic and terrestrial animals, as well as many bird species, including migratory ones. On top of that, treated effluents can provide fast-growing trees with nutrients, as they consume far more nutrients than ordinary trees. All in all, it's hard to exaggerate the benefits of a constructed wetland as a treatment facility. What's also important for us as wastewater treatment specialists is that
Constructed wetlands are usually very beautiful. They are visually attractive and make you feel as if you are walking in a park.
That's true. Miss Doolittle, speaking of which, let's compare two quantitative indicators. A farmland of 1,800 square meters is required to feed one human resident of our planet on a daily basis, according to Food and Agriculture Organization of the United Nations. This is the first indicator. The second indicator is for you to calculate what surface area of constructed wetland is needed to treat domestic wastewater generated by one Earth resident.
Using which type of a constructed wetland?
A horizontal subsurface flow constructed wetland. Could you please write the following on the board? The number of residents whose domestic wastewater enters the constructed wetland equals n. Water flow rate per one resident is 0.3 cubic meters per day. The constructed wetland's depth is 0.8 meters. Substrate porosity is 50%. Hydraulic retention time is 7 days. Please, calculate the surface area of the constructed wetland which can treat domestic wastewater produced by one person. Is the task clear?
Yes, one moment, I'm making calculations. I have the answer. It's 5.25 square meters.
I've never given much thought to how much more difficult it's to feed a human rather than to treat their personal domestic waste.
Yes, but only if it deals with domestic wastewater, putting aside industrial and other types of pollutants. Now I think it's time to discuss the most important feature of treatment wetlands. Please, write on the board. Technical and natural components in wetlands construction.
Professor, here we have to consider how important the work of
We'll discuss it tomorrow.
that's done by engineers and the contribution of biologists in wetland construction. What's the role of engineers?
Yes, it's an interesting topic.
Engineers calculate a wetlands volume, choose the appropriate materials, and build the skeleton of a wetland.
Excellent, Miss Doolittle. Let's do this. You'll tell me everything, but tomorrow. For now, I have to run. See you.
Involves hydro insulation and thermal insulation if necessary.